Today we are going to share with our colleagues about a research outcome focused on improving center productivity by tackling the challenges presented by ultra fine iron ore particle. As you know, ore like pellet feed from the mines contain many ultra fine particles that reduces permeability in the sintering bed. This directly lowers the process productivity just as the global demand for steel is rising, requiring increased blast furnace and sinter ore production. Our study zeroes in on the granulation processes, which is crucial for productivity because granulation control the permeability of the sintering bed. To explore this, we conducted experiments to investigate raw material flow and residence times using a large scale continuous drum mixture simulator. So, as you can go through this setup. Now, coming to the study, we can say that this flow and residence time under realistic conditions has been shown in this slide. We use a large scale continuous drum mixture simulator with dimensions and operational parameters designated to mimic industrial setups. We tested rotation speed from 10 to 25 rpm, that is 10 to 25 rpm, and the drum angles between zero point 0.9 to 9 and 5.4 degree. So there are basically 2 degree, two different setup of the angles, that is zero point 0.9 and 5.4, and feed rates from 50 up to 180 kg per minute, and experimented with various ring dam height at the dischargent. So these are the variables that I want to share in this slide. Now, measurement technique included an innovative pressure stimulus response test using zinc oxide. Now, continuous residence weight measurement and detailed occupation area ratio assessment is being done. We also evaluated the granulation improvements using the granulation index ZI, that is 0.25. Now coming to the our key finding, what we call the droop effect at at low drum angle between 1.8 degree, the raw material layers tapers off and thins as it approaches the dischargent, and leading to a notable reduction in residence time also, that is up to 46% shorter than predicted by traditional model like a Siemens. Okay, so this droop test or droop effect, we can say, is significant because older models were based on longer rotary kiln and higher angles where this tapering was negligible. Additionally, our tracer test confirmed that the raw material moves almost like a piston, showing through cross-sectional mixing but minimal axial mixing, which is key in understanding material flow dynamics here. Now coming to the second key findings, and to address the droop effect and improve the residence time, we introduce a ring dam, regarding which we have just discussed in our earlier slide at dischargent of the drum mixture. Now this ring dam prevent the tapering of raw material layer and drastically changes the flow dynamics. For example, a 60 mm dam maintain a nearly constant occupation ratio along the drum length, while a 120 mm dam significantly increase it, especially near discharge. So we can say that or we can say we can term importantly the ring dam increases the mean residence time from 1.3 minute to a range between 1.8 and 2.8 minutes. These extended the residence time result in better granulation as seen in increase of granulation index GI, that is from 0.25, that is improve in granulation index GI 0.25, that is from 8% to as much as 25%. So thus, the ring dam not only control the material flow but also enhance the overall granulation quality, we can say, by the outcome of this experiment. We further investigated what operating factors influence residence time. We found that slower rotation speed and lower drum angle, that is, slower rotation speed and lower drum angle, both increase residence time significantly. Interestingly, the feed rate alone has little effect on residence time unless the ring dam height is fixed. And we can say that more feed result in shorter residence time due to material backup effect. With the ring dam in place, raw material flow like a liquid over it, changing velocity and pressure of dynamics near the discharge. This understanding let us fine tune. This understanding let us fine tune mixture parameters for optimal granulation outcomes. So we can say that this leads us to a model accuracy to a great extent. The traditional Seaman model predict residence time well at high drum angles but overestimate it up by up to 46% at low angle caused by the droop test. To solve this, we develop a new residence time model that introduce an angle that is psi, accounting for the real material surface slope in the drum. This angle psi depends on rotation speed and drum angle. So this depend on rotation speed and drum angle and is expressed as that is psi is equal to 0.0025 times n times alpha to the power minus 2. Incorporating this psi into the model yield predictions that match our observed data very closely. And also it's improving the design accuracy for modern drum mixtures. So now coming to the our practical implications, we can say that in practical terms, our finding offer a reliable strategy to overcome permeability challenges caused by ultra fine ores. Using a ring dam is a straightforward and effective way to extend residence time and enhance granulation, thereby improving bed permeability and overall sintering process productivity. Adjusting rotation speed and drum angles, that is what two factors that we have come across. Adjusting rotation speed and drum angles allows operators to tailor mixture conditions to meet production goal. Critically, our new residence time formula give industrial practitioners a precise tool for mixture design and optimization, replacing insufficient earlier models. So we can say in conclusion that low drum angles causes the droop effects, leading to a shorter residence time than conventional models predict. Second is installing a ring dam at the discharge and the effectively preventing, or we can say that prevents tapering, increase residence time and greatly improve granulation that we have already observed. Our revised residence time model incorporating the angle psi accurately predict flow behavior in modern drum mixture. So this is all the summary. We can say that these insights into axial raw material flow and control mechanism will help optimize sintering processes further, enabling higher productivity of sinter mixture even with a challenging ultra fine ore blend.